Are you guys ready to see some misbehaving functions? Okay, so in this video we're going to go further into limits and we're going to discuss rational functions. Do you remember what a rational function is? Let's see if you can pull it out of your memory. It would probably help if you try right now. Let's call our arbitrary rational function maybe r of x. What defines a rational function? The key word here is in the first word, rational, ratio. You remember ratio? That means a fraction. So what it is it's the ratio of two functions, and both of those functions are going to be polynomials. This is why it's so very important for you to first understand the form of a polynomial. Because the next step after we look at the polynomials and say, oh, well, you're all very well behaved, is what if we take one and divide it by another one? That gets us into the rational function category. Sometimes they're nice, sometimes not so nice. If you remember from pre-calculus, this is around the time when I started talking about vertical asymptotes. Yeah, when things blow up to plus or minus infinity, and that's not that pretty. Okay, so that's what we're going to be discussing here. But as you learned in the last lecture, the limit of any polynomial, so here we have 2p of x and q of x are both polynomials. Okay, as we learned in the last lecture, the limit of any polynomial is just a plug and chug type of thing. You take the limiting value a as x approaches a, and you toss it in the function, and you get the answer for the overall limit. Now here, I'll tell you that this is the easy part. If we're taking the limit, so first of all, let's say we're consider the limit as x approaches a of the rational function r of x, okay? So I want to consider what the limit is as x gets closer and closer to a of this type of function, ratio of two polynomials. The next thing is if q of a is not equal to 0, which is to say that if you take the number a that the x is sneaking up on and you put it inside the denominator, q, if q of a does not output 0, that would be nice. That would be very relieving to know, because when this equals 0, that's the divide by 0. That's when all the bad stuff happens. If it doesn't divide by 0, there's really nothing wrong with it. So if q of a is not equal to 0, then the limit as x approaches a of r of x, just like for the polynomials, is going to be a simple plug and chug evaluation. And that's the answer for the overall limit. And remember, if we have the fact that the overall limit is equal to something, it implies that both of the one-sided limits are also equal to that, because that's the only way for the overall limit to exist. Okay, so this will be a really nice case that if I'm not dividing by 0, all I have to do is a plug and chug, and that's going to get me the answer for the overall limit. Okay, so let's spend the rest of the time talking about what happens when you plug in a and q of a turns out to be 0. Those are going to be all the bad places. So now let's look at the case where I take the a and I plug it into the q and it equals 0. Okay. Now there's two things that can really happen. I'll call it case number 1 and case number 2. And if I get a 0 on the bottom and I don't get a 0 on the top, that means I'm taking a normal non-zero number, trying to divide it by 0, which is like the smallest of the small things, and so it's going to blow up in my face. It's going to be a vertical asymptote, okay? So the first possibility is if p of a, now I'm talking about p, the top, if I take that same number a and plug it into the top, and that's not equal to 0, then most cases we're going to get a vertical asymptote. Guys, remember that from pre-calculus? Maybe a little bit. We didn't focus on it too drastically, but now it's coming back into play here. So let's take a look at what a vertical asymptote looks like. Let's say my value for a is right here. Let's say it's the number 2. Maybe the function looks like this, and it's blowing up on both sides. That's an example of a vertical asymptote. Or maybe the number is over here. Now let's call it 5. I'm just making these up. It could go like this, where when I'm approaching it from one side, I'm going down to minus infinity. When I'm approaching it from the other side, I'm going up to positive infinity. These are two qualitatively different cases because in this case, although these are both vertical asymptotes, in this case, at least on both sides of the two, they're going in the same direction, which in this case is up. So some people would say that the limit of this function as x approaches 2 is positive infinity, because they're going up all the way to positive infinity. However, this case is a little worse than that even, because if I'm approaching if I'm approaching the number 5 from the left, you can see my function is going down, down, down to minus infinity. But over here, if I'm approaching 5 from the right, it's going up to positive infinity. So this one's even worse than that one, because at least these ones both match. These are both going to positive infinity. Over there, those are going different ways. So that really, really doesn't exist. In all of these cases, when we have a vertical asymptote, we're going to say that the limit does not exist. So when we have a vertical asymptote, I'll just abbreviate that as VA, then the limit does not exist. Okay, so DNE. So if I said, what's the limit of this as x approaches 2? DNE doesn't exist. Some people would say plus infinity, which is descriptive, but the thing about infinity is, it's not a real number, right? Infinity is a concept. It is a conceptual quantity that is larger than any finite quantity that you can name. It's not a real number. So even when it is positive infinity, it still does not exist. Okay, so to simplify it, just answer does not exist. This one, they don't even match. The one-side limits don't even match. Definitely does not exist. Alright, so that's case 1 of the 2 divide by 0 cases. Case 2 of the divide by 0 cases is going to be the opposite of this, which is to say that if P of A, we plug in A into the numerator and it equals 0. But we already said that when we plug A into the denominator, that equals 0. And now you're telling me the top is 0 too? So then, this is what we have, 0 over 0. And 0 over 0 is what we call one of the indeterminate forms. Okay. Why are we talking about any of this stuff? Remember from the first video I told you I'm going to get to the calculus eventually. I'm going to be talking about how things are changing in time. And one of the very most important things is the concept of the derivative, which is how something is changing at an instant of time, instantaneously. And what we have here, the ratio of 0 over 0, this turns out to describe the motion of change at an instant in time. This indeterminate form is the most important thing that you're going to take away from the whole chapter on limits. That's what's going to move forward as we define the derivative as in a limit form. You're going to get a 0 over 0 form. Okay, so this is really important for what we're headed toward later. So let's look at that in a little more detail when we have the 0 over 0. What is 0 over 0? Is it just 0? I wish it was that easy. Well, I don't wish it was that easy, because then the magic of calculus wouldn't happen. The thing about 0 over 0 is it can be a lot of different things to a lot of different functions. It's indeterminate. That means I have not determined it yet. And I want everybody to take a moment to understand that the word indeterminate is not the same thing as does not exist, DNE. Does not exist is determined. It is determined to not exist. Indeterminate, 0 over 0, means I can't even say. Does it exist? Sometimes it's going to exist. Sometimes it's going to be just a real number. Sometimes it's not going to exist. It's like, I can't determine any more information until you give me some actual functions and I'll work through it and kind of feel out what's going on with the 0 over 0. This is a very questionable, yet to be determined. I'm really not sure what it is, and it's not the same thing as does not exist. Okay? So let's look at an example of a couple of these different things. Now, I'll start with case 1 to make sure that everybody understands that. Let's say that we have the rational function ratio of 2 polynomials, x plus 2 over x minus 8. Okay, notice that there's a poly on top, poly on bottom. They both happen to be linear, so I've got the ratio of 2 lines here. Okay, do you guys have your graphing calculators? I require a graphing calculator for Math 148 because it's for your own advantage. Go ahead and graph this function right now. you're really going to be a lot better off in this class if you have a picture of the function. Just like how when I drew you a picture, it was easier to figure out what the limit was, right? Okay, so take a minute to get out your graphing calculator and get yourself a picture of this function. Just a little picture, snapshot. And I got a picture of the function, it kind of looks like this. Now maybe your graphing calculator doesn't draw the dotted line there, but hopefully once you've looked at it, you understand that what's going on here is that the function has values pretty much for every number x that I put in, except when x is equal to 8. If I put in the number x equals 8, I divide by 0 right here, and that's that case that I want to focus on. And this is case number 1, where when I plug in 8 here, I get 0 on the bottom, but I get 8 plus 2, 10 on the top. So that means the numerator is not equal to 0, but the denominator is equal to 0. Okay, so let's consider the limit as x tends toward the number 8 of r of x. What do you think the answer is going to be for that if I asked you that question? Does not exist, right? That's right, because it's a vertical asymptote. So you simply answer does not exist. Even if it looks like they're both going to positive infinity, if they were both going to negative infinity, or if you have a little of both. If you've got a vertical asymptote, the limit answer is does not exist. Okay? And you can see that from the picture too, so it's really going to help if you graph it. If you don't want to graph it, if you're just against graphing for some reason, I've seen some people who are, and it's personal choice. Here's what they call the analytical or algebraic method, is that you always try plugging in. Okay? If you have a function that's not piecewise defined, like you just have one blurb of what the function is, if you plug in and you get a number out, a normal number, that's the answer. It's as easy as that. That's what happens on the polynomials. That's what happens on the rationals when we're not dividing by 0. Okay? So let's just try plugging in ho-hum. Pretend you can't see that there. X is equal to 8. That's the limiting value that I'm approaching. So I get 10 over 0. Does not exist. 10 over 0, what's that? Well, it depends on which way you approach it. It could be going towards minus infinity. It could be going towards plus infinity. It's really a little of both. The thing is, it does not exist. Okay? So if you see a number that's not 0 over 0, the answer does not exist. Okay, so now let's change the function a little bit, and let's see what we can get here. What if I give us a new function, maybe with a quadratic on top instead of a linear, and then the same bottom, x minus 8, there's going to be a problem when x is equal to 8 there. Go ahead and graph that function. I'm going to want to consider, of course I want to consider the bad spot. By the way, if I ask you for any other limit, like if I ask you for the limit of this function as x approaches 0, keep in mind the plug and chug is always in effect. Plug it in and see what happens. Okay, so let's do this easy one really quick. If I ask you what's the limit of r of x here as x is approaching 0, if you plug in 0, you get 0, 0, minus 8. You get minus 8 there. That simplifies to 1. So the limit of r of x as x approaches 0 is just 1. If you plug and chug and you get a normal number, that's the answer. Okay, and that's for functions that are not piecewise defined. We'll go into piecewise defined functions later. But now, for example, let's try the limit as x approaches 8, okay? So, of r of x, I'll just, plug in the numbers here. Let's see, we got 64 minus 56 minus 8, and then we get 8 minus 8, and let's see, 64. Hey, wait a minute, 0. Hey, wait a minute, 0. 0 over 0. That's right. That's the other case I'm talking about, is when you get the 0 on the bottom, but you also get the 0 on the top. I don't know what it is. It could be anything. Seriously, it could be any real number right now, and it needs further investigation. It's an indeterminate form. Okay? Which ways do I have to help myself investigate functions? I have plug and chug. I already did that, and I know I got myself in a sticky situation where I have yet to determine the answer. Graphs. Oh yeah, don't forget about the graphs. The graphs are super helpful. Seriously, try it out. Go ahead and graph this function and see what the function looks like. It may not be what you expect. Okay, so you can get out your graphing calculator, kind of get a graph of this function going on, and if you do graph the function and you're playing along, did you get something that looks like that? A line? Does it look really like a line? What's the deal with this? What's going on? This equation looks pretty complicated, and yet when I threw it into my grapher, I just got a line. Now it turns out what your calculator is giving you back is not exactly correct. Do you guys remember what the domain of this function is? Do you remember domains from pre-calculus? Domain is all the numbers that are okay to plug in. Okay? What is the domain of this function? See how much you remember from pre-calculus. What is the domain? It's all real numbers except, can't use 8 because 8 would give me a bad spot there where I'd be dividing by 0. So the domain is all real numbers except x equals 8. So whatever my graph gives me back, I have to understand from my knowledge of calculus and pre-calculus that the number 8 is not in the domain. So there's really a secret hole here, even though you might not see it on your grapher. Okay, so be really careful with that. That's a subtle point, but it's true. For example, if I ask you the question, what is r of 8? The answer is, not 0 over 0, don't give me that. Does not exist. Yeah, I don't know what it is. It's indeterminate right now, but this is not in the domain. Okay, this is not, the number 8 is not in the domain, so the functional value does not exist. Okay, but what we're going to go into a little further here is the topic we've been talking about, the limit as x approaches 8 of r of x. Now that's a little different. X is equal to 8 is not in the domain, so I have an open circle where x is equal to 8. However, is the number 7.9999999, is that in the domain? Yeah, it's not equal to 8. What about the number 8.000000001? Is that in the domain? Yeah, it's not equal to 8, right? So all the numbers that are super, super close to 8 but not equal to 8 are in the domain, which tells me that I might actually have an answer for this limit. If I do have an answer, the answer will be, how is the output of the function behaving when I'm very, very close to but not equal to 8? Okay, see if you can guess that now. What if I'm really, really close to 8 but I'm not equal to 8? It looks like just from the picture that I'm getting very close to whatever the height of this hole is. On this side too, I'm getting very, very close to whatever this height of the hole is. If you do have it graphed, can you guess what that height is just by looking at your graph? That's going to be the answer for the limit. It turns out that this limit does exist and it has an answer, but for us to really get the answer, that's for sure, I don't want you to actually give me the answer from your graphing calculator. I don't want you to have to eyeball this stuff. The answer might be a fraction. The answer might be something a little weird. And I'm going to want the exact answer, not an approximation. Okay, so what happens when we get the 0 over 0 form? Let's try factoring. Factoring. Did you ever think that you were going to have to use that again? You might have to use that in this class, so I hope you remember factoring. What we're going to do is we're going to take the original expression of r of x, and we're going to see if maybe that bottom term, x minus 8, maybe that'll cancel out if we try factoring the top. Okay? So go ahead, you're going to need this skill. So if you don't understand the skill, search for factoring online and get some refresher on how to factor a quadratic, and let's see if you can factor that. Okay? Here's the factored form right here, x minus 8, x plus 1. Now let me just check to make sure that numerator is still correct. X squared minus 8x and then plus 1x makes minus 7x. Minus 8 times 1 is minus 8. Okay, that's the top. The bottom is still minus 8, and would you look at that? I get the same thing as on the top as I do on the bottom, and that's why I got 0 over 0 when I plugged in x equals 8, because this is a 0 here, and then I'm multiplying by a 0 there. So that's why I got that, okay? So since, or I should say, when considering the limit as x approaches 8, it's okay to cancel, which is to say that when I'm talking about the limit as x approaches 8, so x is not equal to 8, but it's something very, very close to 8, but it's not 8, then I can cancel these on top and bottom. I actually cannot do that when x is strictly equal to 8 because you're not allowed to cancel zeros with zeros. That's not allowed. It's like if you had an equation, something equals something else, and you multiply both sides by 0, you're not allowed to do that, okay? Because it just makes everything disappear. But as long as these things are not 0, sure, they're close to 0, but they're not 0, and they're also equal, I can cancel them right out. So it's okay to cancel, which is to say that when I'm considering the limit, this thing is equal to x plus 1. Because the top and the bottom factors of x minus 8 canceled. Okay? Now let's see what happens if I plug and chug, because this looks like a polynomial, and that's really not too bad, right? Okay, x equals 8, so let x equal 8, and then what did I get? I got the number 9. Now for those of you playing along in your calculator, did you actually guess by approximation and graphical observation that the height was approaching 9? That's why calculators are awesome. So you should definitely be graphing things. I'm going to allow graphing calculators in all the quizzes and tests that I give. Look at that. It's another total way for you to see the answer, to check your answer, and to have full confidence that your answer is going to be correct. Okay? So notice that we were talking about the 0 over 0 indeterminate form, but the actual answer we got was 9. In other cases, the answer might be minus 1. In another case, it could be the square root of 7. The indeterminate form can result in any of the real numbers. It could also possibly result in plus or minus infinity. That's why it's not determined yet. Okay? So this is a really sticky form. We're going to be discussing it at length because it is the key to the limit definition of what we're going to call the derivative later. So make sure that you understand this and very much understand this factoring rule. You might want to review a little bit. Okay, so why don't I end this video with an application. Haven't really gotten to speak about business too much yet. So maybe this question might seem familiar if you start to do the homework assignment for this week. Let's go into an application. Example. Let's say that R of t is the rate of production of some toys in a toy factory for 0t to 8, okay? Where t is the number of hours past 8 a.m. Okay, so usually people working an 8-hour shift, they might start on the normal day shift from 8 a.m. to 4 p.m., so that's 8 hours of work. And let's say that we have a function R of t in a toy factory, and that exactly describes how many toys per hour are being output by the workers in the factory, or by, let's say, one typical worker in the factory at a certain time t. Okay? So right when I get there fresh at 8 a.m. in the morning, I would plug in t equals 0. Maybe it's time for lunch, I'm getting hungry, it's noon. Halfway through my shift, I would plug in t equals 4. Oh, I'm about to get off work. I've done 8 hours. I would plug in t equals 8 for 4 p.m. Okay? So what I want to do here is I want to compare what is the rate of production right before my lunch break, or let's say right around my lunch break, versus right before quitting time. Okay? So let's compare the rate of production near, let's say, noon, 12 noon. That would be t is equal to 4, lunchtime. And 4 p.m., that's quitting time. That would be t is equal to 8. Okay? So I want to compare them near it, and that's really, you could actually plug in these numbers because those numbers are in the domain, that's fine. But I want to use limits because limits is the topic of the section. So really, I'm going to ask you mathematically for what is the limit as t approaches 4 of r of t. And I'm also going to really ask you what is the limit as t approaches 8 from the minus side of r of t. Okay? This is really what I'm going to ask. Hey, how come you asked t equals 4 overall, but you only asked t tending toward 8 from the minus direction? Why'd you do that? because numbers that are greater than 8 are not in the domain. You see, 8 is the borderline of the high end of t. 8.5, not in there. Sorry guys, there's no overtime in this job. So I have to only consider the limit as t approaches 8 from the minus side. Okay? But for t equals 4, I could be less than 4, I could be greater than 4, I could actually be both. So I'm allowed to ask for the overall limit here, but not so much here because numbers greater than 8 are not in the domain. Just a little technicality. Okay, so from everything we've learned so far, why don't you go ahead and try to answer this question, which is just comparing these two rates of production. Did you get an answer? Okay, I got an answer. My answer here, as I approach 4, was 1.89. And then as I approach 8 from the minus direction, 0.98. Where did I get those numbers? Remember, when we're talking about rational function, the first thing you want to do is plug and chug. If you take the number 4 and you plug it in here and you get a number, that's not weird, it's not dividing by 0, it's not 0 over 0, that's the answer. If you take the number 8 because you're approaching 8 and you put it in there and you get a normal number, that's just the answer. Okay? So it turns out in this real life problem we didn't have to deal with any vertical asymptotes. We didn't have to deal with any indeterminate forms. Really, vertical asymptotes are not that common in business applications. However, the indeterminate form is very important as we move ahead to define the derivative. Okay? So it's not just for nothing.